Okay, and so please congratulate the speakers or presenters as you see them during the day. With that, we'll move on to our first talk. We have a set of 4 awesome talks lined up for you. And the first talk will be Jaap Nienhuis, who will be speaking on 2 worlds on a single planet, long-term coastal geomorphological data versus models. Chad, do you get up the presentations or do I? Sorry.
All right. Yeah, that one. Thank you so much, and thank you, Julia, for the introduction. Very happy to be back at Systems after many years. So I'm going to talk about 2 worlds, and those 2 worlds are data and models. So over the past many years, I've tried to integrate in my lab group at Utrecht, I've tried to integrate data and models, and I think you can learn a lot about trying to integrate these 2. I'm a coastal geomorphologist, so all of my models kind of sit in that realm of coastal geomorphology, but because of the diversity of this audience here, I'll try to keep it a little bit methodological and talk about the methods that we use to try to merge these two worlds. But before I get into the how we do this, first a little bit into why you would want to have models to do things in coastal geomorphology, and this is from 2 papers from Brad Murray. Right, and you can do 2 things. You can be interested in predicting coastal change, and if you want to do that, you can have machine learning models, you can have simulation models that really nicely represent a particular coastal system, a particular delta, for example. But there could be another purpose as well, right? As academics, you would also are interested in explaining things about coastal geomorphology and explaining and understanding things about the world. Well, we try to bridge data and models, and I think in doing that, we try to also do both things at the same time, right? And how do we do that? Well, we first make idealized process models, so very simplified models that avoid many of the complexities of any individual delta system or coastal system. So in this case, this is a Del3D model of a river mouth with idealized boundary conditions, idealized setup, idealized initial conditions. And what we try to do is we try to kind of marry this model with observations here, right? And we're not going to do this one-to-one, so we're not trying to simulate any delta in particular or any river mouth in particular. But in this process, in trying to marry these 2 things and the ways we try to do that, I think you can do both this prediction element of coastal change and also this explanation element. So really try to gain some understanding about the world. And also I'll go through several of these projects where we try to marry these two different things. One, for example, is from a PhD work that I did with Andrew Ashton quite some years ago now, where we're really interested in river channel orientation, right? And this is a nice wave influence delta. This is the CM model that probably some of you from the Aspen summer school know about. And you can force this 1-line model with some river sediment flux, and you can see nicely this delta channel migrating into the direction of incoming wave energy. Right, and you can see that this might kind of look like this particular delta, this Ombrone delta in Italy, and that is also migrating into the direction of incoming waves, but it's very different from this delta here, the San Francisco, I think, that is flipped. So north is not this way. Anyway, this is another delta that is oriented differently. And in trying to learn something about river channel orientation, you can't really do this one-to-one comparison against any delta in particular. And what we do instead, and I think in that process we learn a lot about river channel orientation, is we try to run many different model simulations and try to come up with some non-dimensional framework that allows us to really get into the mechanics of what sets these river channel orientations. So rather than just plotting 100 different model outputs and presenting those, but we try to come up with our non-dimensional numbers, in this case, an updrift migration index and a downdrift migration index, that you see really nicely kind of spread out the different types of channel orientations that you might find on deltas, all the way from downdrift migrating channels to this updrift migration that you saw on this GIF earlier, right? And you can see that with these two different non-dimensional numbers, you really get a very smooth signal in your model output. And what it then also allows you to do is find these non-dimensional numbers for real deltas and plot them in the same framework, right? So in this case, you really married both observations and also very simplified models. And in some cases, you see that it nicely matches with the color of this dot represents also the orientation of this channel that aligns with the contour space of the simplified models. And in some cases, it doesn't match. And I think in both cases, you'll learn something, right? There might be something else that is driving channel orientation in this case, or it might give you some assessment about model or data uncertainty at the same time, right? So in both cases where it matches and where it doesn't match, you learn something. What you can also do is then predict this coastal change, right? You have this non-dimensional framework, so you can say, well, what if some of these indices might change in time? If you have an increase in sediment supply, for example, do we then see a coincident increase or change in the channel orientation from going from downdrift away from the wave to into the incoming wave direction? But you can see that when you run a simulation, you can see this switch in time. And you can also then move your delta through this non-dimensional space and really do this space for time substitution, right? You can then verify this with the uncertainty that you find from your model data comparison. So with this space for time, I think you can get into that other objective, and that is predicting coastal change. So this is one example. You can do this in many other types of things about deltas or other coastal geomorphologies. And this is from a paper from a former postdoc, Pani, who's now at AFIT in Colombia. And we developed this methods paper about kind of formalizing this Galloway triangle of delta morphology that probably many of you know, into these three different sediment fluxes that define kind of what makes a delta, right? This is a very simplified schematized delta, a river mouth with some incoming river sediment flux, some movement by tides back and forth, and some export of sediment away from the river mouth due to waves. And from those three different sediment fluxes, we can then cast them in this non-dimensional triangular framework. And again, do this for both predictions and observation. In this case, this wasn't even a simplified numerical model. This was an analytical model that allows us to go from sediment fluxes to predictions about some aspects of delta morphology, in this case, shoreline angles, some channel widening metrics that I won't go into the details of, and also the number of distributary channels. Right, so you can make this prediction, but of course, in this same framework, you can then also put some observations. Right, so you go to different deltas, and you say, well, for this particular delta, we extract these sediment fluxes and these shoreline angles, and then we get some assessment about the model uncertainty. And this is again for one delta, but I think it's this effort is strengthened if you include many more deltas. Right. So in this case, for example, we extracted some predictions observations for about 40 deltas around the world. You can see clearly where the model doesn't work and where it does work. Right. So it gives you some sense and some comfort also in where your model works and where it doesn't work. And at the same time, you learn something. And also, if you're really tired of triangles, we now have a square. Right. So this was a reviewer said, like, well, perhaps you can use these metrics and just make it into a two-dimensional square. So there is a delta square now as well. Right, and this is with an analytical model. You can do the same thing with more full complexity Delft3D models. This is from a paper recently published by Connor Broadus, who's here in the audience. Really trying to do this Galloway triangle game again with some observations of real deltas where we can extract these metrics, and then also doing this for Delft3D simulations. That, of course, you're never going to get a one-to-one comparison, but some of the kind of higher order metrics that you find in terms of number of channels, channel mobility, shoreline shapes, you can then try to predict with this Delft3D model. And again, in this framework, you can also do space for time, right? You can plot this, and if there's a delta here, and you say, well, this delta perhaps is affected by deforestation and increases sediment fluxes, we would then anticipate an increase in river dominance over time. Perhaps this delta is forced by sea level rise that increases the tidal prism and makes the delta more tide dominated, perhaps now affected by flow reversal at the river mouth. There's an increase in storminess, for example, that would push the delta to this wave dominated corner. And if all of those things happen at the same time, perhaps this delta change is really an integration of all of these three different factors. And the net change that you see in terms of delta morphologic change is traveling through this non-dimensional space right there. Right, and again, I think this case is strengthened when you include more and more field observations. So, for example, when we have, in this case, thousands of river deltas across the world, we can then be a bit more confident in the type of morphology that we expect for this delta right there, and then how it travels and changes its morphology as it travels through the space to then arrive at this other location. All right, so just to broadly sum up some of the reasons why I think this approach works, and then I'll get into some of the downsides later. But I think you can do a really great job in doing both predictions and also learning something about the world in marrying simple models and global data. I think when you do this, when you increase your data availability, you also increase the range of calibration parameters, right? You're not testing against one fluvial sediment supply, but against a range of fluvial sediment supply, a range of sea level rise rates, et cetera, et cetera. And by expanding that range, I think you can do a much more robust test of your model. I think you also have a smaller selection bias, right? You're not picking any individual field site, but you're really expanding beyond and doing many deltas at the same time. You can detect more subtle signals because you have more data to compare it to. And then lastly, something that I'm getting into now also with Julia, who just introduced me, is that if you do this and have global data and learn something about the world, you can also perhaps try to make some implications that are relevant for global change, including some biogeochemical cycles. And this is a working group that we're in now called Leaky Deltas. We had a meeting about a month ago where we're trying to kind of combine and see what the relevance is of coastal geomorphology and deltas for the carbon cycle in this case, right? But having this global data then allows you to upscale and really get into global fluxes and how global change is then influencing, for example, the carbon cycle. So some of the limits, and this is a simulation. I think it would run when I turn it on. I think that the limit is nicely illustrated by, no, let me try to press play. So this is, before I press play, find my mouse, there it is. No, that's unfortunate. No. Oh. So this was supposed to be a model simulation. Where you can see this is a delta from the sides, and that's fed by a river sand supply. There's some sea level rise that was supposed to come up. And this delta would have grown over time. And what you've seen is some auto break or auto retreat happening at some point, right? So that it's no longer some linear model that you do, but you have tipping points and tipping points in strong linearity. And I think that might be very difficult for a space to time or space for time substitution for different models. One way to get around that, I think, is testing your model not against different deltas around the world at current day, but perhaps get into time series. So this is a nice paper from Doug Edmonds, testing very simple models for land loss, fitting it to observations from Barataria Bay as a subdelta of the Mississippi River Delta, and in seeing what type of components really explain the land loss that we observe here for the past 50 years in the Mississippi Delta. So again, this is a very simple model, in this case tested not against a broad range of deltas that we observe now, but against time series of delta change. This, of course, works when you have very dense and nice time series of deltas, which are fairly limited, of course. What we're trying to do now is expand this to other deltas and expand also this concept in time. So these are some shoreline trajectories of different deltas around the world. You see that in the past or early Holocene, there was a lot of transgression, of course, because of high relative sea level rise rates. Slowly, bending towards regressive regimes and growing deltas over the past 6,000 years. So with these time series, I think you can also compare that against models while doing these space for time at the same time. But that's really kind of an open question that I'd like to get your input on as well. I think there's a lot of clever people in this room. So what we're trying to do is combine this space for time that I talked to you about, this non-dimensional framework where we can compare different deltas and get more confidence in our assessment of what delta change look like, and combine this with some time series that we have for any individual delta, and then really expand that across the globe. So what if we have, in this case, a time series of 10 deltas? Can we then use this information to get some of these this info also for other deltas around the world? That's still, I think, an open question. We try to do this for river deltas, but we're also trying to do this for barrier islands, combining simplified models like this one with time series of paleogeography, in this case of the Dutch Wadden Islands, where we have some transgression rate over time, but also perhaps try to compare that to the Chandeleur Islands, for example, or the Outer Bank, and do that in one big non-dimensional framework. That would make me very happy. So to conclude, what we've been trying to do is marry these process models, simplified models, with many observations, ideally global observations, into some non-dimensional framework. And I think in doing that, it forces you outside of the realm of pure models, outside of the realm of pure data, and really get into global predictions and global understanding as well. Thank you.
And we have time for questions. Wow, that's all. Hold on, I have a question. I was curious about, and I'm not a geomorphologist, as much of a geomorphologist as you are, for sure. And when you showed the triangle diagram, and there was this lack of points in the middle. If you
Not
could
the
speak
first one to see that.
Yeah.
Yeah. So I'll go back. This one here, right? No, this is what work with Pani. This one, yes. So I think there's a statistical effect in when you have three numbers that expand a broad range, then you're more likely to have one number be much higher than other numbers. So you're forcing deltas toward the edge, and it's relatively unlikely statistically that all three are going to be the same order of magnitude. But if you just expand this and do this for many other deltas, at some point, if you have enough deltas, you're going to find some that are in the middle.
Thank you.
Just a question about your, toward the end, the time series of deltas, retrograding and prograding in that one. The timing of the switch to prograding, I think, is interesting, because it sort of postdates the maximum sea level rise, which of course that's going to be important. And I wonder if this is in part due to increased sediment load due to deforestation, agriculture across all these areas.
That's a very good question. We've pondered that as well. Let me get into the time series.
Your kind of modeling could kind of take that into account.
Yeah, so initially we thought it was an effect of delta size a little bit, because the trinity of smaller deltas is making this transition a lot later. And I think generally a lot of the deforestation we expect to be much later, although you're right that there's probably a lot of Roman deforestations in some of the Mediterranean deltas.
And the Chinese ones too are going to be early also.
Yeah, no, it's a good question. So of course it's not just sea level rises that are forcing these delta changes.
I think I saw another hand up, but I wasn't sure.
Thanks for the lovely talk. In terms of expanding these frameworks back into needing the stratigraphic record to start giving inputs for delta model data, how do you see dealing with signal shredding compared to like the nice satellite time series you can work with modern deltas?
It's again a very good question. I've had some conversations with people that do outcrops, and in general, one of the difficult things we had, and it's also comparing models and data, is that the type of data they get is not the type of predictions that we make with the model. So we get into like we want shoreline angles, downstream widening, other sorts of that. You don't get that really from outcrops. So that was one difficulty. The other difficulty that you rightly point to is, of course, like what signals are preserved in the stratigraphic record. I don't know. I feel a little bit hesitant in, I don't know, blurting out something in front of this audience.
Time for one more question.
Wonderful talk, Jaap. In the beginning of your presentation, you showed simplified models compared to natural examples, right? And of course, nature is super complex. One of the big drivers, I think, for natural deltas is the volume of, where sediment get deposited. If the ocean is kind of deep, you don't get in much delta propagation. But I'm assuming that's not in your simplified model, right? So how can you handle things like that, or is it just not possible to handle those?
I think it is. So so that question is a little bit related to other aspects. So our analytical model predicts morphology independent of delta area, right? So you can have a very small delta that is river, tide, or wave dominated, or a very big one. And of course, if you're a deeper delta, then you would prograde slower, and you might also be smaller. And in that sense, it's a little bit independent of this framework, and we have some other models to do delta area prediction. So there's another model would be more appropriate for that.
I think let's go ahead and switch speakers. Thank you.